All good. Do you see screen share?
Perfect. Thank you.
Okay, great. Hi, everyone. My name is Maxim Sharbaika. Thanks for the invitation. I am a senior software developer at Haivision, and today I would like to present you the secure, reliable transport protocol. Okay, how can I do next slide? So what is SRT? SRT stands for Secure Reliable Transport. It is a protocol built on top of UDP. It provides bidirectional data transmission with mechanisms for packet loss recovery and latency management. SRT is content agnostic and thus can transmit any type of content in its payload. It is a transport protocol in the first place, and the payload can be securely encrypted. SRT can be used in multiple cases. At the moment, the major purpose and use case of SRT is low latency live video contribution and distribution. SRT offers mechanisms to keep constant end-to-end latency, to recover packet losses, to handle packet jitter, and so on. To enable real-time live streaming, some packets that fail to be recovered within the specified end-to-end latency have to be dropped. This is also handled by SRT in the corresponding operation mode. This slide presents more cases SRT can be used in. Being content agnostic, SRT can transmit any payload. For live video contribution and distribution, SRT usually transmits MPEG-TS, RTP, or elementary streams in its payloads. Another use case is transferring files and segmented streaming formats like HLS and DASH. In this case, SRT ensures every packet is delivered to the receiver and that there is no control of the end-to-end latency in this case, because real-time delivery is not required for this kind of transmission. The third potential use case of SRT is tunneling. Again, SRT is content agnostic, and therefore it can tunnel TCP packets, HTTP requests and responses, and almost any type of other type of payloads. Message exchange is one more use case. Exchanging some metadata, control data, custom voice commands, and so on is also possible with SRT. All the described use cases are covered by these three operation modes of SRT: message mode, live mode, and buffer mode. Message mode can be used to transmit messages that span over several packets. Live mode is a subset of message mode with additional features to enable real-time live stream delivery. And the third mode is called the buffer mode. It is used to open a connection, transmit a single and large piece of data, and then close the connection. For example, if you have 1 GB or 5 GB file, you can open one connection, start sequential transmission of this file, and once the transmission is finished, you just close the connection, and that's it. So before going deeper into the overview of SRT features, I would like to share some motivation. Why you should use SRT, for example. And so SRT was created in 2013. In 2017, SRT was made open source and free for public usage. And at the moment, SRT is one of the most widely used protocols for live contribution and distribution. Companies using SRT are joining the SRT Alliance that currently counts more than 350 members. And only last year, more than 100 new companies had joined the Alliance. This slide presents the latest survey on the video transport protocols usage conducted recently by Haivision. It can be seen that SRT is used by a decent part of respondents, and the relevance and application of SRT has grown enormously as the amount of live video distributed over the public internet increases. At the moment, SRT is implementation-driven protocol, and it is open source. So the library is hosted on GitHub. It is free for commercial use. And all the features of the protocol that are being developed are implemented straight away in this library. So you get the latest and the greatest. We have a community of more than 350 companies, all using this exactly library. And there are 63 contributors to this project on GitHub. So by using SRT, you get a library used and tested by a large community. And in comparison, if like a company would like to implement this kind of library on its own, it would need a dedicated team of specialists in this area and QA departments. And imagine the QA department compared to the 350 companies using this library, and every day submitting issues and reports and feature requests. So SRT is very easy to integrate into your project because library provides POSIX-like API. So if if your solution already supports TCP or UDP sockets, then all you need to do is, roughly speaking, just add SRT prefix to each TCP system function call, and that's it. And of course, project is alive and active. So this bar chart on this slide shows the amount of issues and pull requests being opened and closed every month. And we try to respond to incoming issues and requests as fast as possible and keep the level of issues remaining open more or less under a certain limit. In addition to enormous amount of commercial products, the library is used in a variety of open source projects as well, like VLC, FFmpeg, GStreamer, OBS Studio. Wireshark and TSDAC analyzers also support SRT, and package managers like Homebrew, Debian, NuGet, and VC package also support SRT. And there is also an ongoing effort to make SRT a specification. There is already a huge document called SRT Technical Overview, which describes the protocol and algorithms in details. And this year we brought SRT to IETF to have an official RFC specification. And this initiative is currently in the progress. So the first internet submission draft was submitted on March 9th of March. This slide presents a matrix of SRT features that addresses the most common tasks and issues associated with live streaming. These are connectivity, access control, security, content delivery, and connection bonding. I will go through them group by group. And let me start with the first set of tasks, which is connectivity. Connecting two peers together without using a third party in a public internet is often very tricky. Modern-day networks use NAT and firewalls. While SRT offers firewall traversal mechanism, it lacks NAT traversal. We are potentially interested in integrating with interactive connectivity establishment in the future. Connection migration and network switching are features that also could potentially be added in the future to distinguish multiplex streams. SRT already operates with connection IDs, which could be used to perform this kind of switching. So no significant changes in the protocol are required. It is more a matter of specifying the procedure and mechanisms to do this. Let me go into the connection establishment a bit deeper. SRT establishes a connection via handshakes. There are two types of handshakes. The caller-listener handshake is illustrated on the left side of this slide. It is used to establish a connection with a known server that has its UDP port open and the corresponding firewall rule configured to enable incoming traffic. In this case, caller initiates a connection by sending an induction handshake. The listener sends a response handshake packet back to the caller. Peers exchange their configuration and the connection is established. There are also use cases when there is no possibility or it is ineligible to change firewall configuration and open certain ports. SRT offers a special rendezvous handshake procedure shown on the right. In this procedure, both parties send a wavehand handshake to each other, and through a cookie contest, they decide who is to become a caller. These outbound handshake packets traverse the firewall to allow incoming UDP packets from the peer. In both cases, SRT connection establishment takes about 2 round trips. Stream configuration is exchanged in the handshake, including latency negotiation, encryption, and so on. And a notable feature here is that additional user-defined data can be provided in the corresponding stream ID field of the handshake packets. And this brings us to the second set of tasks, which is access control. Consider a client wants to connect to a streaming server and request a certain resource. The streaming server needs to authenticate the clients, probably share the stream definition for the requested resource, and start sending the data. SRT currently supports this use case. Here is an example of this use case. Media server has a database of users and their unique passwords and a set of resources it provides access to. So clients can connect to the media server, provide its username and the resource identifier it is requested. It tells if it wants to receive the resource or, for example, publish it. The user tells his passphrase to SRT, then SRT sends a connection request to the media server. And the password itself is, of course, not sent to the server, but a key derived from the password is sent instead. So the media server is notified about the connection request through a listener callback function. The server finds the user in its database and tells SRT a password that should be used by this user. SRT derives the key from this password, and if key matches, then connection is established. If there is a key mismatch, then the connection is rejected. And once the connection is established, the server already knows the resource being requested by the user and can, for example, start streaming from a file archive or provide an access to some live streaming that is taking place and so on. This slide provides more details on how SRT Access Control works under the hood. SRT handshake packets has a dedicated field called Stream ID that I talked previously about. This field holds up to 512 characters of custom user data. The content is not restricted by SRT, but SRT provides the so-called SRT Access Control guidelines that suggests a format to exchange some useful information like username, request resource ID, stream content definition, and so on. In this example on the slide, client provides its username, tells that it wants to publish SRT SVA overview.ts, and by default it means live streaming. So live stream will be published under this name. And of course it tries to connect with a unique passphrase. Once the connection is established, content can be transmitted over a public network so that anyone can access it. SRT offers IS encryption of the payload of data packet to secure this content. A pre-shared password is used with a password-based key derivation mechanism to establish an encrypted connection. Other automated key distribution methods could potentially be also adopted in the future without notable changes in the protocol. So only dedicated handshake fields should be changed, and maybe a handshake. So IS encryption is applied on the payloads of data packets. Payload is encrypted with a IS cipher in a counter mode. And the counter mode is suitable for continuous stream encryption, and it permits random access decryption of or more or less any packet, so that packet losses are tolerated. If you lost a packet, then you can still decrypt further packets of this sequence. And unlike the payload headers of SRT packets are not encrypted, this allows processing of packets without knowing the encryption key and without getting access to the payload. And so the encryption workflow is a bit complex, and it is separate topic. So for more information, please refer to the SRT Protocol Technical Overview. The link is on the slide. I would just, again, would like to know that SRT can potentially be extended with other encryption and key exchange mechanisms without dramatic changes of the protocol. So it's already flexible enough to do it. The fourth set of tasks is content delivery. Like any lossy network, public internet suffers from packet losses, packet reordering, jitter, and the variant end-to-end latency. Packet losses introduce artifacts in the video. The variant end-to-end latency may cause unstable playback speed, freezes, and so on. Some lost packets may not be retransmitted in time. They have to be dropped to enable real-time streaming. All of this has a major impact on the quality of experience, and SRT addresses these problems. Also, SRT is doing congestion control, flow control. It is network friendly, and of course, there is a lot of room of improvement. And again, SRT is flexible enough to this kind of improvements. To tell about content delivery in details, I will start with SRT packets. SRT packets are transmitted in the payload of UDP datagrams. This slide shows the placement of SRT packet in UDP payload. Every SRT packet has its own header and packet contents. There are two types of packets in SRT: control packets and data packets. Packet type can be distinguished by the corresponding bit flag F highlighted on this slide. Control packets are used to interchange control data, which includes handshake, acknowledgements, and so on. Data packets are used to transmit the actual payloads or forward error correction packets. This is the structure of SRT data packet. The timestamp field is common for both control and data packets. It indicates the relative time when this very packet was submitted to SRT on the sending side, and SRT uses it to control the end-to-end latency of the transmission. Apart from that, data packet has a dedicated field that specifies the sequential number of the packet. It is used to determine losses in a sequence of data packets, and requests for retransmission can be done based on these packet sequences, or receiver can acknowledge that certain amounts of packets were received based on these sequence numbers. SRT uses regular acknowledgement packets to acknowledge the reception of a certain sequential number of packets. ACK packet has a dedicated field called last acknowledged packet sequence number, so it refers to the sequence number of the packet that I showed in the previous slide. Acknowledgement packets are sent periodically, by default every 10 milliseconds. They also carry some useful information estimated by the receiver, like RTT of the link and link capacity estimation. And for high data rates, the receiver should send acknowledgements more often. In that case, a light acknowledgement packet is sent on every 64 data packets received. Light acknowledgement carries only the last acknowledged packet sequence number to reduce the overhead, and all those fields marked with red on this slide are not transmitted in this light acknowledgement packets. So-called automatic repeat request mechanism is based on negative acknowledgement packets that receiver sends back to the sender. Thus, the sender finds out there was a packet loss and it can retransmit lost packets. NAC packets or loss reports are sent once the packet loss was detected. After that, a periodic loss report is being sent to let the sender know an updated state of the receiver. Each NAC packet can hold several sequence numbers of lost packets and even ranges of sequence numbers. For live streaming, SRT provides an additional benefit of recovering the timing of the source VBR streaming that can be distorted by network transmission. This recovery of timing helps decoders and playback devices to add only minimal additional latency for decoding, while the whole management of the end-to-end latency is performed by SRT, and the application doesn't need to implement or handle it itself. Everything is available out of the box with the protocol. This slide presents a mechanism used to keep a constant end-to-end latency in the live streaming mode. It is called timestamp-based packet delivery. Based on the packet timestamp, receiver knows the time this packet is to be delivered to an upstream application. The receiver keeps the packet in its buffer until the delivery time has come. Knowing this latency, receiver can try to recover a missing packet up until the delivery time of the next data packet in order. In this example, packet number 1 is received after half round-trip time, which is the one-way network delay in this case. So this packet is kept in the buffer until its delivery time and delivered to an application after a known delay. Even when the network delay changes or some packet jitter happens, packet will still be delivered to an application with a fixed end-to-end latency. So the latency starting from the packet was sent and up until the delivery to the application. So in this example, packet number 3 was lost during its transmission. Once the packet number 4 arrives, the receiver detects a loss and requests retransmission of this packet. In this case, packet number 3 was successfully retransmitted before the delivery time of the 4th packet. So it is present in the outgoing sequence of packets that goes to the upstream application. If a lost data packet is not recovered, by the time to deliver the next data packet has come, the receiver will drop the missing packet to preserve the end-to-end latency. For example, in this case, retransmission of the 3rd packet fails within the predefined latency, so the packet will be dropped. Dropping a packet means no further attempts to recover it are made, and an upstream application will not get this packet. The following packets are being delivered to the application instead. This mechanism of dropping a data packet is called too late packet drop or TL packet drop. And this is how SRT enables low latency real-time delivery of any type of content, but usually in PACK-TS. This slide shows the efficiency of this retransmission-based recovery mechanism. This experiment was carried on a custom network setup. RTT of the link was 54 milliseconds. SRT was used to stream at 7 megabits per second. X-axis shows the value of the receive buffer latency configured relative to RTT value of the link. So the value of 1 means buffering latency equal to 1 RTT or 54 milliseconds. Artificial network impairments were introduced, a packet loss ratio of 4% in one case and 8% in another case. As you can see, at latencies below 1 RTT of the link, the amount of unrecovered packets is similar to the loss ratio on the link. The latency of 2 times RTT or 108 milliseconds in this experiment allowed to recover the most parts of lost packets. In order to properly handle fluctuations of RTT and different types of congestion on real networks, the recommended latency value is 4 times RTT, which is enough to recover almost every lost packet. Besides ARQ that I just described, SRT offers other possible packet recovery options like forward error correction and bonded SRT connections. In case of forward error correction, SRT provides an extension and certain packet formats to apply any custom forward error correction algorithm. In case of connection bonding, several SRT connections can form a single bonded connection. Thus, a certain type of redundancy can be utilized to increase the chances to deliver packets, or at least increase link throughput. 3 bonding modes will be supported in the upcoming version of SRT library: a broadcast, main backup, and load balancing. This slide illustrates the FEC packet recovery option. SRT provides so-called packet filter API. So it's API that can be used to implement any forward error correction algorithm. And this packet filter is placed between the UDP socket and the inputs of SRT processing. So when packet is received on UDP socket, if it's a control packet, packet filters just eats it and uses it to recover previously lost packets, and then it can, instead of this packet, give out the recovered or reconstructed packet for SRT to process. And SRT library currently implements one packet filter option, which is forward error correction. So in brief, forward error correction uses a matrix of payload packets. On this diagram, it is shown with white colored boxes. So white colored boxes is the matrix of actual payload packets, and this matrix has additional column and additional row of FAC recovery packets. If one of the packets is lost in a row, this recovery packet can be used to recover it. And as you can see, in this example, there are 50 payload packets. So it's 10 by 5 matrix, 50 payload packets and 15 FEC packets. This means that the overhead of the transmission would be 30%. And of course, there is also additional delay that has to be introduced with this matrix. It depends on the size of the matrix and on the bitrate of the stream, because you need to wait to the very last FEC control packet to understand if you can recover more payload packets or not, and you just drop them. So, for example, if you would like to stream at 10 megabits per second with this kind of FEC matrix, 10 by 5, then you will have to add additional 68 milliseconds of latency to your transmission. Another recovery option is bonding, and one of the modes of bonding is broadcast mode. In broadcast mode and in bonding in general, you have several SRT connections that you bond together to get one bonded link. So in case of broadcast, each bonded link is used to transmit a copy of every packet. So it's like full redundancy of the link. And as illustrated in the slides, if one link loses one like certain packets, another link loses different packets, then they can be combined to get zero packet loss in the output. And of course, each link can additionally apply loss packet retransmission-based recovery and FSC recovery and so on. So it's additional increase in the transmission. Another bonding mode is backup mode. So in backup mode, you again have several links, but only one link is considered active. So all the rest links are kept alive, but no transmission is happening over these links. And over the active link, you transmit packets. Then once, for example, this link gets broken, SRT switches its transmission to one of the backup links based on the priorities. And it can just continue transmitting. And this way, the upstream application, again, gets all its packets, even when one of the links is broken. And the third option is balancing. Balancing mode can be used to increase the combined throughput of the links in the bonded connection and to balance temporal congestion on the links. So, for example, let's consider you have like two LTE connections, each allows 10 megabits streaming, and you want to stream, for example, 16 megabits over it. So you can, in normal network conditions, you can stream 8 megabits over each link, and your overall throughput will be 16. And when one link has congestion, you can temporarily increase the streaming rate on another link to improve the delivery. This slide presents the comparison of all the available packet recovery options. So in terms of overheads, loss-based packet retransmission provides low overheads that is comparable to the actual loss ratio on the link. FEC provides relatively high overheads, as you have seen previously. And bonding in the broadcast, for example, mode provides some overheads that is multiple to the number of links in the bonded connection. Recovery for IRQ is, fairly speaking, great. For FEC, it's relatively low. FEC can recover low losses. So based on our experiments, if you have packet losses of 3%, you can get most of your packets recovered, but still some amount is not recovered. So if you go up above these values, then it's like the matrix is distorted very much and you don't have enough control packets to recover it. And in case of bonding, you just have redundancy and you have bulletproof packet recovery. So latency for IRQ is the same as for bonding. And it's, for example, 2 RTT for low latency case and 4 times RTT is a recommended value. For FEC, it's very low, and it's the advantage of FEC. It can be used, for example, for unidirectional links when you have really low loss ratio on the link, like, for example, satellite links. Then you can recover your packets, and you don't need the feedback channel to request for retransmissions that will add additional latency to this. So IRQ can be used generally in all types of networks. FEC is more for unidirectional links with low percentage of loss on it, and bonding can be used when you have multiple links and you want to somehow utilize its resources. So the remaining features I briefly talked about is stream multiplexing, for example. SRT manages connection based on the dedicated SRT socket ID field present in every packet. For example, data packet and the handshake packet are shown on the slides. By means of this SRT socket ID field, SRT provides bidirectional data transmission and stream multiplexing, making several connections on a single UDP link possible. And SRT also, SRT library and SRT as a protocol provides very useful statistics For example, a receiver estimates link RTT, bandwidths, and SRT library provides API to retrieve all the statistics. You get this values RTT bandwidth, you get packet received, sent, packet lost, packet dropped, and so on. So the whole list is on the specification on our GitHub, and these statistics can be used to understand what is going on in your network and your transmission. For example, if you are seeing some artifacts in the video, you can check SRT Statistics. SRT tells you that there were no dropped packets on the link. Then you can, for example, blame encoder or some other multiplexer that's these artifacts happen. But if you see, for example, that there are losses and there are drops on the link, then it's network conditions, and you need to go deeper into this. So SRT Statistics, SRT positive and negative acknowledgement mechanisms, all of them together can be utilized by various congestion control algorithms. Which congestion algorithm to use is the decision of the implementation. In non-live streaming modes, the existing SRT library uses a variation of the additive increase multiplicative decrease algorithm, relying on the link capacity estimation and loss reports. Live streaming is a special case of congestion control because you have a known input bit rate and you need of your source streaming and you need to preserve it. So congestion control should do all the best to preserve the source streaming rates, while the pacing and retransmission decisions can be adjusted by congestion control. Also, center may decide to drop some packets prematurely to reduce network congestion. This is roughly what the existing live congestion control implementation does. And of course, there is a lot of room for improvement here. And again, SRT is very flexible. It provides an API to add additional congestion control algorithms, and congestion control algorithm that will be used for the transmission is negotiated in the handshake. So it's very extensible in this case. This slide is an example of how file congestion control works. So it was a transmission over Azure network, and there were a certain amount of congestion on the link. So as you can see, for example, the above graph has blue lines and orange lines that tell about the number of lost packets and the number of packet retransmissions. And the red line, which is the packets that were dropped, so that means the upstream application didn't receive it. So this amount of dropped packets is at 0 in this transmission mode. And SRT increased the sending rate when link conditions allowed that. Once it gets a certain amount of congestion, it stops a bit at this point. So if the amount of loss on the link is pretty low, so below, for example, 2%, SRT will try to keep on the existing sending ratio, sending rates, to see what will happen next, because normally this amount of loss ratio on the link is pretty normal. So in this case, SRT then increased the sending rate. It went into a bit of congestion, again not very high, but still decreased sending rates. Then network conditions came back to normal, and it again increased, and so on. So this is how this congestion control works, and it provides good throughput for the network. Really trying to utilize as much available bandwidth as possible, and at the same time by avoiding congestion. So the retransmission overhead is really low in this case, which is a good indicator that congestion control works well. So this was all the presentation I had to share. If you have any further questions after the discussion section, please feel free to contact us on Slack of SRT Alliance. Also on GitHub, you can create issues, feature requests, and you can reach me directly via email. On this slide, you can see it. Of course, there is SRT RFC draft proposal. You can go over to check what's going on, how certain things are implemented, and SRT technical overview, and of course, the library itself. So thank you.